will be metal oxide or whatever it is. And inorganic means sometimes you may have a polymer layer. So polymer layer also you have to use it for sensing layer. So there is a basically entirely different phenomena if you are using organic phenomena or if you are using metal oxide layer as sensing layer. So in metal oxide, what will be the case? Due to mass loading, your frequency will be shifting down. But if you are using polymer, then polymer due to the stiffness, it will increase your frequency. So sometimes you have an increase in frequency, like that is the case of resistance. Your resistance increases or decreases based on the type of gas. Here your frequency will be increase or decrease based on the type of sensing layer. If it is metal oxide, it will reduce your frequency, shift your frequency down, or if it is polymer, it will increase your frequency up. Then we have a calorimetric type of sensor. So you can see these different type of sensor and what kind of sensing layer they require and what is the sensing principle. So in our case, we have a change in mass or density, and due to change in mass and density, there is a change in the frequency. Clear? So you have to identify what kind of sensor you want to fabricate, and based on that you have to select particular sensing layer and how this sensing layer play a major role to change the principle of that particular sensor. So what are the key challenges? Detection of very low concentration agent dangerous to the human health has become the challenging task. Means how we have to sense the particular gas at the trace level. Clear? So that is very challenging. Then electroacoustic transmission mechanism based sensor possesses high sensitivity to sense various biomechanical agents is on VOC is also challenging. So many scopes are there. So you need to also it is very design and development of portable devices. Portable devices means you do not require any setup to, because see, you can't go to industry with setup. You can't say industry I need a setup to show my performance. So what you need to do, you have to make your device portable. Means it is portable and you can utilize directly for the what purpose. For example, you want to measure the glucose level. So how can you fabricate this device? So that should be non-invasive, means without blood. How you have to do? So for that different methods are there. So your device should be what? Non-invasive, means it based on your what we can say your VOC level, that is extract from your exhale from your mouth. Based on that, so you have to fabricate your device non-invasive based sensor. Clear? But it should be portable. You did not show your outcome in laboratory. Clear? So how you can make it as a portable? There is also still challenges. Then we have different volatile organic compounds. So how we have to design a sensor to sense these VOCs for industry as well as in our environment sensing. So we see we have different type of sensing methods. So we have optical, calorimetric, electrochemical, thermoelectric and acoustic. So throughout the lecture we have discussed about PCM, SO and MO. And MO we have a F bar and SMR F bar. So we have another sensor that is metal oxide. So we discuss here how this metal oxide will work. So what we have in this metal oxide, earlier what you have this ceramic tube, inside ceramic heating element. What is this? This is heating element. So you have to generate heat, and because see why you need require heat to excite your sensing layer. If you are not excite your sensing layer, it will not sense your gas. So for that earlier you required a heating element to excite your sensing layer. And outside what you have? Outside you have an electrode. Through that you have to measure the change in the concentration of your gas based on the change in the resistance or current of your device. So we have a 4 electrode, one electrode, this one and this one, that is for your heater to make increase the temperature of your device, and 2 electrode for measure the performance of your device. So here you can see this is the heater coil, and this lead wire and this lead wire is your electrode, and this center SNO2 is your sensing layer, because this is the metal oxide layer, and this metal oxide layer always used for sensing layer. So this is the exact device, metal oxide gas. So what we have in this case, we have bottom side C, we have a bottom side, we have a heating plate. Clear? So this is my heating plate, and here we have a for electrode for heating this substrate, and top side we have this electrode. That is for what? Measuring your current or resistance. Clear? And on top of this electrode, what you have? You have a sensing layer. So what will happen once some gas will be directly evaporated to sensing layer, then there is a either you have a change in the your depletion layer, and based on that your current or resistance will be changing. So then you have to measure. So this is the principle how you have to can have. So in the resistance case, what you have, there is a change in the resistance because of change in the depletion layer. Then we have a how we have to use this mirror based F bar for the sensing purpose. So what we are here, we have molybdenum and Si-O2 layer we are using here for designing the mirror, and this is my PIB layer. So here I am using polymer as a sensing layer. So what is my sensing layer? PIB, polyisobutadiene is my sensing layer. So what is the principal layer for sensing layer? My frequency delta is changed, and this delta is changed due to the change in the mass of my device. How this mass will be changed? This mass will be changed by density of sensing layer. How this sensing layer density will change? When my gas is passing through this PIB layer, it will absorb to this polyisobutadiene layer, that is my sensing layer, and due to this mass loading, what will happen? This density will increase, and once this density will increase means what? This delta will increase, and I will measure this change in delta. So you can see what is your concentration, because what is the parameter you are increasing here in the sensor, you are increasing your concentration of your gas. So once you increase this concentration, what will happen? There is a change in the density, and what will happen? Initially you have a density of your sensing layer, that is raw polymer, that is fixed. But once you increase this concentration of gas, what will happen? We are here we have a sensor performance. So this is my regulator performance without sensing layer. So now if I will deposit a sensing layer top of the my electrode, then what will happen? This sensing layer will be work as a mass sensor. Loading layer, what will happen to my device? Frequency response, it will shifted down. Why? Because the sensing layer will be created as a mass loading layer. So my frequency response shift from here to here. Understood why it is shifted? This response is without sensing layer, and this response is with sensing layer. Now I have this device response, and I want to check how I have increased my concentration. So before that, I want to check that how if I have a, because see, I can't control my thickness strictly during the fabrication. For example, for my mirror. So what will happen if I have a 5 to 10% variation? For example, I am looking for 1 micron thickness of silicon oxide layer and 0.7 micron thickness of my molybdenum layer. And let's suppose it is changed by 5 to 10%. So here you can see, initially we decided this thickness should be lambda by 4. So this is the performance parameter. But for example, let's suppose this is vary by molybdenum thickness is vary by 10%. So what will happen? Your performance, your frequency will be increased. Clear? So what we have, there is no degradation in your sensor performance, but your frequency will be little bit shift, but it will not response. Why? Because in sensor response, what we are interested? We are interested only in the change in the frequency. Whatever it should be 2 GHz, it should be 2.2 GHz, it will give me a same response. But it will impact when you go for filter design. Because in filter design, if you are looking for 2.4 GHz and due to the variation of mirror layer, if your frequency will change, then entirely whatever you are targeting, you will not achieve that particular filter. So where it is important? It is important once you design a filter. Sensor it will not bother, because we are in sensor we are bothering about it should be not there is a spurious mode or higher harmonic mode we do not require, because it will disturb my sensor performance. So here we are checking what will happen if there is a variation in the thickness of my mirror layer. Then here we can see how now once how I have to optimize this sensing layer, because you can't randomly take 100 nanometer, 200 nanometer, 500 nanometer. So what you need to do, you have to optimize the thickness and measure the performance. So directly you can't enter into a fab lab and you have to do so many iterations in fabrication. So before that you have to check your thickness with different combination and you have to check the performance. So see here, I have start with what thickness? I have start with 170 nanometer. So in this case, I kept my sensing layer 170 nanometer thickness. What happened? There is no change in frequency. Clear? Then I double the thickness of my sensing layer 170 to 340. Means little bit there is a change in the frequency once I have increased the concentration. What I am doing here basically, here I am increasing the concentration of gas. Means what do you mean by concentration? If I increase the concentration, basically what I am increasing? I am increasing the density of the sensing layer. So if you are increasing the density of sensing layer, what will be the response of your filter, resonator? Its frequency will be changed based on the concentration of gas. So see here, little bit change in the frequency. Now we increase from 340 to 510 nanometer. Then you can see we have a very good shift in my frequency. Then again I increase 510 to 680 nanometer. Then you can see here frequency is still shifting, increasing their layer. But what? There is an extra harmonic modes are generated. Means these are the unwanted modes and it will disturb your performance of the sensor. So what we can do, which thickness we will select for my sensing layer? Can you tell me? What will be the better thickness? If you want to use sensing layer, then what thickness you will be used? It is in front of you, all result. You tell me which thickness you want for your sensor. Which one is better? No idea. Obviously 510. What we want in our sensor, it should give us a very high frequency shift without any higher harmonic mode. Clear? So if my delay is more, then I can easily visualize my change in the concentration of the sensor. So see, in this case there is no change in frequency. Then how can you measure the concentration? Which concentration it will give a particular gas. So in this case, in 340 there is a change in frequency, but very little. But in 510 we have a very good shift in frequency as well as there is no generation of higher harmonic mode. So I optimize my thickness to 510 nanometer. So once next I enter into the fab layer, what will be my sensing layer thickness? I will use 510 nanometer for my sensing layer. Like that we also optimize my variable thickness for particular 2.4 GHz So like that, I have to optimize my sensing layer thickness also once I design my sensor. Understood? Why I will not give? Because this, what will happen? This also created a response of your resonator. So this thickness will give me a better sensitivity. Do not see this speed. You get answer. You can tell me which thickness will give you a good sensitivity. 0.7 micron will give you, or 1 micron give you a good sensitivity. Just now we discussed what we want to make sensor highly sensitive. What we want? We want to increase frequency. And when it will increase? When your isoelectric thickness will be less, because my frequency by 2 dB and V is fixed. What is in your hand? Thickness. So 0.7 micron thickness will give you a good sensitivity. Understood? So see here. What is here? There is a change in the frequency, and here you have a change in the concentration. So for example, you are having a 50 concentration. Here concentration 50, 100 and 150 ppm. Then what will happen? This 0.7 micron thickness nano sensor will give you a highest change in the frequency. Why? Because its frequency is high. Understood? Then next what I have a graph that is earlier we have discussed. So you can see here what will happen if you have a different thickness of your sensing layer. But see here, your change in frequency is also increasing with this 680 nanometer also. But what is the problem with this 680 nanometer? It also having a higher harmonic mode. So that's why we avoid this. We will select this 510 as my sensing layer thickness. Then next, once you achieve a very good sensor with highly sensitive, then what you need to do? You have to check the selectivity. Whether it is give same selectivity to all the gases, then it is not there. For example, I want to design a sensor for NO2 gas, and it will give same performance for all gases. Then what is the utilization of that sensor? So what I need to do? I need to check the performance of my sensor with other gases also, and whether it is selective to NO2 gas or not. So here I design this sensor for DCM dichloromethane gas. So I will check whether it is give better performance in the case of DCM or not. It is selective to that one or not. So here you can see this performance for DCM is better as compared to C. In the case of chloromethane or methyl oxidane, there is no change in frequency, because see, this reference is without any gas. So whatever, if you have CM or methyl oxidane, there is no change in frequency. But in the case of DCM, you have a change in frequency. So it is selective to DCM only. So what we need to check? We need to check the selectivity of my sensor also. So here you can see the selectivity response. It is very sensitive to or selective to only DCM, and for other gases it will be work as a noise. It will be created as a noise. Clear? So that's how we have to design our sensor with the help of. So what we seen here till now, we have seen how to design sensor, then after design how to optimize it, then how to design a mask to fabricate the device, and how to fabricate, and then what kind of characterization you have to perform, and once you have in your device in your hand, then what kind of application you have to utilize with the help of this device. So we have seen how we have to design filter with the help of this device, or how we have to design sensor with the help of this device. Understood? So here you can see performance of this device with other devices also. So see, if I have increasing the frequency of my resonator, my sensitivity will be increasing. So if you need highly sensitive, is what you need to do, you have to increase your frequency. Then you can see here, this is the sensor with 842 megahertz, but its sensitivity is very low. Clear? That is published by another researcher. So you have it all about your optimization. Once you have, because until unless you have not optimized your device, you will not get whatever you want. Clear? So what is conclusion about this part? We have discussed about literature, what are and how we have to utilize it. Then we have seen of simulation and how we have to optimize 2D and 3D device. And once we optimize, we will move to fabrication of that device, and then further after fabrication, we have to see the characterization of that, and we see the performance of fabricated device. So, if you have any doubt, you can ask. No doubt, then you have to write at least fabrication step. I am giving you one device. Clear? How you have to fabricate that device? So you have to write a fabrication step. Very small device I will give you, so it will help you to understand the fabrication step. Okay? So So now see here, what is this? This is, I have a sensor. So this is my silicon substrate, and this is my SiO2 layer, and this area represents my heater element. What is this? This is my heater element. Yes. What is this? My heater element. And what is this? This represents my SiO2 layer, that is for insulation purpose. Okay? This is my insulation layer, and then I have an electrode. These are my electrode. And over this electrode, what I am having a sensing layer. What is this? This layer is my sensing layer. Clear? You have idea? What is my this? This is my silicon substrate. Over this, I deposit my SiO2 layer. Then I have to deposit and pattern my heater. What I am doing? Deposit and patterning my heater. And then I have the insulation layer. That is again, it may be your SiO2 or silicon nitride, Si3N4. And depending on you, whatever you can choose. And then you have a top electrode for measuring your current and resistance. These are the top electrode, and over the electrode you have this sensing layer, that is your metal oxide layer. Maybe your ZNO, or it may be your WO3 tungsten oxide, or maybe your indium oxide In2O3, or it may be titanium oxide. It could be anything. Clear? So now I will give you a top view. Without top view, you can't decide about fabrication step. So what could be the top view of this device? So what I have this silicon substrate, and over this silicon substrate what I have a SiO2. So SiO2 throughout over the complete silicon substrate is oxidized with oxide layer, that is your SiO2. Then what you need to do, you have to deposit and pattern your heater. So this is your heater. So this is your heater. Okay, it is not like that, it is somewhat like that. This is your heater. Then what I have? Then I have a insulation layer, oxide layer, to isolate this heating element with my active area of device. So what I will do, I will deposit oxide throughout this substrate, and what I will do, with the help of lithography, I have to open this area, because if I will not open this area, then how can I make contact and hit this silicon wafer? So what I will do, with the help of lithography, I will open this area. So what I will do, I have a entire wafer is what? Here everywhere you have oxide, only except this contact. So here everywhere you have a azium, everywhere you have a oxide. Clear? Then after that what you have a patterning, deposit and patterning of your electrode. So what is your electrode? So it may be your here. This is contact for your electrode. This is my heater, not this line heater. This is connected to here. Okay, so this is my IDP electrode. Clear? And then over the IDP electrode, what I have the sensing layer. This is my sensing layer. What I have this square portion indicate my sensing layer. Understand? So what I need to do, with the help of lithography, I have to open this contact and this contact to make a contact for your heater and for your device. And see, the rest of the what? You have a coated with oxide layer, and for electrode what? Where you have to deposit your electrode? Over this oxide layer only. Clear? See what is your structure of electrode. Let's suppose this oxide layer is we have deposit where? Where we deposit this? Over my heater. So let's suppose this is your heater here. This is your heater contact. What is this? This is your heater contact, and the remaining area, what you have? You have a oxide. Then you have to have your contact for electrode. So this is my electrode contact, and how I will make it? So this is my IDT. That's how I will fabricate this. So this is my IDT electrode. Clear? And over this IDT electrode, I have this sensing layer. So this is your IDT, and over this IDT you deposit your sensing layer. Now you tell me how you have to define your fabrication step. At least tell me how you have to fabricate your heater. One step you have to write. At least you should understand how you have to fabricate your heater. What you require. I am opening my fabrication step, so that you will be understanding very easily. Yeah, this one. This step is same you have to follow for designing your heater. What we are doing here, we are designing my top, we are patterning my top electrode over the oxide layer. Similar here what we are doing, we are patterning my heater over the oxide layer. So what is the step? First, what I will do? First, I will deposit my heating element. Because substrate I have oxidation already over the substrate. What I will do? First, I will deposit my heating element. So what you will be used for heating element? Any metal there? It will be nichrome, nickel plus chromium. You can use. So if you use nichrome, so what you need to do? You have to deposit your nichrome layer. Clear? So once you deposit your nichrome layer, what you will do next? After depositing your nichrome layer, you have to spin coat photoresist over your nichrome layer. So once you spin coat your photoresist, then what will you do? You have to go for soft baking or pre-bake. So for that you have to go for soft baking for 225 minutes at 90 degrees centigrade. Then you have to use UV lithography. So you have to fall UV lights over your substrate. Then what we have in between your substrate and UV light, you have a mask plate. Because we have seen how we have to design mask. So that mask plate we have. So what this mask plate will do? Because we are using here bright field lithography. So what will happen? Wherever we have a bright areas are there, UV light exposed directly, and wherever we do not have a dark, wherever we have a dark area, UV light not exposure to your photoresist. So brighter area will become softer and darker area will become strong. So once after UV lithography, we will put my silicon wafer into a developer. Then what will happen? Unexposed area of your photoresist will be intact, and exposed area photoresist will be developed into a developer. So now you have this photoresist left, and your nichrome layer will be open in this area and this area, and this photoresist will be creating as a masking layer for your nichrome, because this nichrome we want to protect to make my heater, and we want to remove this nichrome and this nichrome to pattern my device. So what will happen? I will put this vapor. Where I will put this vapor? I will put this vapor into my nichrome HN, and this nichrome HN will etch out by this area and this area, and it will be intact because it will be protected by this photoresist. And finally, what I will do? I will put my this silicon vapor into a acetone bath. So this acetone will, what will do? This acetone will be develop this photoresist, and finally you have a only heater pattern onto your device. So at least you tell me what is the top view of your. So this is top view of my bottom electrode. So what is your top view of the heater? Can you tell me after patterning what will be the top view of your heater that is available in that board? All of you try to do. What will be the top view of your heater? This one only. What do you have? This is your top view. I'll show you. Then this is your top view.
So suppose if you want to deposit the aluminum night, suppose that is like as a burger reflector in the substrate. So how to suppose we have to give the substrate here.
Yeah.
So in that we have to deposit the burger reflector.
Yeah, the reflector. Mirror layer. Yeah. So what we will do? We have already this device without this metal oxide layer. So what we will do? First we will deposit molybdenum as my reflector layer. So for that I will use sputtering. So with the help of sputtering, for that I do not require any lithography because I want this mirror layer throughout the vapor, because this mirror will work for all devices, same mirror. Clear? So for that I do not require any lithography. So first what I will do? I will deposit my molybdenum layer, and over the molybdenum layer I will deposit my SiO2 layer. So like that I will deposit 3 mirror one by one. Why I require 3 mirror? Because based on the whatever the highest acoustic impedance, if you have very high acoustic impedance ratio, you will achieve it into a 2 reflector also. Clear? So for reflector we do not require any lithography, but number of steps increasing for your deposition of metal or oxide. Clear? So it will increase your number of deposition steps, not a lithography step. Okay. But problem with this mirror is that you can't strictly control the thickness of each mirror, because we see we have to maintain the strictly control the thickness of the mirror layer. If you not control, then what will happen? It will shift your frequency. So it is okay if you are going for sensor, it is okay. But if you are going for designing a filter, then you will not get the performance what you are expecting. Okay? So yeah. What will be your top? So see, what is I have this silicon oxide over my entire silicon wafer. So what is my heater? So this is my heater. So this is my heater. So after my lithography, I have only this structure left over my silicon substrate. Understand? What will happen? This complete nickel chrome will be etched out. Because why? Because I have in this area I have a photoresist. What I have? So this nickel chrome will be intact, and remaining nickel chrome will be etched out because of agent of nickel and chrome. So similar here you can see this photoresist will protect your nickel and chrome below this, and remaining area what will happen, your nickel and chrome will remove, and finally you have only nickel and chrome below the photoresist only. So like that, after patterning my heater, what is my structure? That is my structure. Understood? Yes? So what step required? Same step required to pattern my heater. Understand? Yes or no? Then what I need to do? I need to deposit my metal electrode to check my performance of the sensor. But I can't directly deposit my electrode directly over the heater. What will happen? It will short. So for that what I required? I required a insulation layer. And what is my insulation layer? Oxide or nitride. So either I can use silicon dioxide or I will go for silicon nitride. So what I will do? Generally I will completely deposit my oxide layer or silicon nitride layer. How I will deposit oxide layer? Now I can't go for thermal oxidation. So for that what I will use? I will go for PECVD. Clear? So with the help of PECVD, what I will do? I will deposit oxide layer or nitride layer throughout this complete wafer. Then you can directly deposit your metal electrode over the oxide layer, or you require a lithography for your oxide layer or insulation layer. Is it required or not? You tell me, you required a lithography for your insulation layer or not? If yes, then why? If you require lithography, why you require? If not required, why you not require? Yes, yes. Yeah, that is okay. But why you require lithography for your oxide layer or insulation layer? Can you tell me answer for that? No, my question is whether we require lithography for this insulation layer or not. Because see what we are doing, we have this. No, that's not right answer. See, yeah, you want to say something? Yeah, very good answer. How do you make a contact for your heater? If you cover your heater bed with oxide layer, then how can you make a contact? So what we need to do, we need to open a window for my heater contact. So what I will do, I will deposit oxide from the wafer and with the help of lithography. Same step I will use. What I will do, I will use same step and I will open only this window. This window and this window. Now this is not visible to you. This area what you have? Here you have a oxide. Only this area is open window. This window and this window is open for making your contact for heater. So how will you achieve this? For achieving this contact, again you have to go for lithography process. Clear? So now tell me what will be your structure. Can you draw? At least 2 to 3 candidates draw the next structure. What will be the next? After this, what will be the next top view of your device? What will be the top view of your device? So this is my silicon substrate. Always I have a oxide, and now I have only this window opening, and all over the other portion what I have entirely oxide. So I am opening these two contacts with the help of lithography, and I can easily make my contact for the heater. Otherwise, how can you make the contact for heater? Understood? Then after that, next step is we are going to deposit my what? Depositing my IDP electrode. So what I will do next? Again, same lithography step I will use to deposit my IDP electrode. So what is your IDP electrode here? So this is my IDP electrode. So how I catching this? Again. So this is what? This is not your heating element, heater element. Where is your heater element? Somewhat here you have a heater contact. This is your heater contact, and this is your heater contact, and here you have a contact for your IDP. Clear? Understand? So now we have to pattern this my IDP electrode for my measuring the current or resistance of the device. So I have this IDP electrode. So again, see, in lithography you have to open this window and this window both. If you are not opening this window, then what will happen? Again, how can you make your contact with heater element? Clear? So now after deposition and patterning of your IDP electrode, what is the trophy of your device? This is the trophy of device. Clear? Then what is the final step of my fabrication? I have to deposit and patterning my sensing layer. And what is my sensing layer? It may be metal oxide, anything. Titanium oxide, tungsten oxide, indium oxide, or whatever you are selecting a layer as a sensing layer. Clear? So what will be the step next? How can you make? So you have a simple square window of your mask. So what will be the case? It is after deposition and patterning, what is the trophy of your device? Can you imagine? I am drawing there final view of my trophy of my device. What is this? Contact for heater or contact for your IDP electrode? What is this? Contact for your heater. Then what I have contact for my IDP. So understand? This is the cross-sectional view and this is the top view. So what you have, you can't see the heater. From top, you are not able to see your heater. Why? Because you have a insulation layer or oxide layer over this heating element. What you can see only, you can see these two pairs for your opening for your heating element. So only you have these two pairs for your heater. And you can see your IDP as well as this is what? This square is your Z. So this square represent your ZNO, titanium oxide, whatever your sensing layer you have. Understand? Clear? sir, still I am not able to understand these steps, I can help you. See the cross sectional view, top view, and you try to correlate it with this fabrication step. In all steps, I have to go through all steps. Without performing all these steps, I can't complete lithography. If I want to go for lithography, I have to go for all these steps. Clear? So now you tell me if you have any doubt wherever, sir, yeah, I have doubt how you fabricate this thing, how it is possible. If you have doubt, you can ask. So finally, this is your top view. This is top view and this is your cross-sectional view. How this cross-sectional view help you to check the compatibility of material with underlying layer, whether particular agent of top layer is compatible with below layer or not. Like that, what we have a nickel and chrome. So this nickel and chrome, what we want here in nickel and chrome, we want to remove this nickel and chrome. So below this nickel and chrome, what you have? Oxide layer. So whether this nickel and chrome HN is compatible with SiO2 layer or not. So if it is compatible, then directly we will go for bright field lithography. Then after nickel and chrome, we are depositing a what? We are depositing a oxide layer and again patterning this oxide layer, and we will see that whether this oxide agent is compatible with your nickel chrome or not. If it is compatible, again we will go for bright field lithography. It means what? We do not require any lift-off process. After that, what we are going to do here, we are depositing my IDT electrode, that is your chrome gold or aluminum, whatever. But we can't go for aluminum because we are fabricating a sensor with metal oxide. So it will be, instead of your metal contact, it will create a oxide layer, metal oxide layer. It will generate a aluminum oxide. So generally we prefer chrome gold metal contact. So once we deposit and pattern by this chrome gold, what I am looking, whether it is compatible with my oxide layer or not. So here oxide layer is compatible with my chrome gold HN, that is hydrochloric acid. Then again over the chrome gold electrode, what I am doing, I am depositing my ZNO layer. That is my sensing layer. But that layer I can't deposit and pattern with the help of what? With the help of bright field lithography. Can you tell me why? Because if you are using titanium oxide, it's okay. But if you are using zinc oxide, then same agent you have to use for etching your chrome gold also. So what will happen if you patterning your sensing layer, same time this electrode plate also will be disturbed. Understood? So what will you do in this case? Whether you can go for it or not. No. Why not? Because once you pattern this, then during that time what will happen? Your chrome gold agent directly, ZN also will be in touch with your IDT electrode also. So for that, what we have to do, we have to use lift-off process. So in lift-off process, just we reverse this fabrication step. Instead of depositing the layer, first we have to coating the PR, then do the lithography, and then we have to deposit the sensing layer, and after that we have to go for lift-off process. Understood? So like that we have to finish our fabrication process. So if you have any doubt, you can ask. Yeah.
Rather than selling
Yeah.
in this fabrication process.
Yeah.
So is it successful or not?
Yeah, you can do anything.
So what is the comparison between using the polymer or same kind of
error is sensitive to that particular polymer or not. Clear? So with the help of that we can understand. So what type of publication available based on your polymer as a sensing layer or based on metal oxide as a sensing layer? Both we can use. Any other answer you want to ask? Questions? Yeah. No. So in next section we will see simulation. How we have to do simulation in COMSOL. Simulation is there. Then this is also available online, so you can download the COMSOL and later you have practice for COMSOL simulation. If you have any doubt, you can contact to me, no problem. Okay. So next we will see COMSOL simulation. How we have to design this device.
Okay. So solving should be done after 4 o'clock. 4 to 4:10. 4:10 we will start. Okay.